Hello everyone, my name is Jiayu, and I'm from Northwestern Polytechnical University in China. My co-authors are Professor Shen and Professor Chang Honglong. Today I'm honored to present our work on the topic 16-micromachined-Gyroscope rate beyond accuracy limit by 1.9 times without bandwidth reduction. MEMS gyroscope is an angular rate sensor that has been widely used in many fields, such as robotics and autonomous driving, due to its small size, low cost, and so on. However, the low accuracy of MEMS gyro limits its application in high-end fields, so how to improve gyro accuracy is a key issue in this field. It has been a consensus to improve gyro accuracy through gyro array composed of multi-gyroscopes and information fusion algorithm. One important research direction is the common filter-based gyro array. It was first introduced by Jiyao in 2003 years. Then this method has since evolved into several directions, such as multi-stage filters combining KF with other state estimators, KF algorithms based on various state models constructions like first-order markup, unknown input decoupling-based KF, orthogonal gyro arrays, and so on. These methods have improved gyro accuracy beyond the basic KF. However, the core step of KF, the addition of prediction and correction, is an equivalent low-pass filter, leading to reduced bandwidth and inaccurate dynamic measurements. Multi-sensor fusion is another research direction, which can improve gyro accuracy without bandwidth reduction. Recent methods focus on calculating weight coefficients based on the optimization of different statistics, such as minimizing variance, Bayes instability, or wavelet covariance. However, these methods exist accuracy limit due to constant weight coefficients derived from above optimization. The common accepted accuracy limit is the square root of n, where n is the number of gyroscopes. This means that it is difficult to combine high accuracy with small size, low cost, and low power consumption. Therefore, breaking through the traditional accuracy limit of weight fusion is significant. Our idea is to use variable weight coefficients instead of traditional constant weight coefficients. From the perspective of fusion accuracy limit function, the only factor that can be adjusted is the weight coefficients. Yes, this. Take the fusion process of two random variables as an example to observe. Mismatches will occur between the residue errors and the weight coefficients in constant fusion, resulting in fusion residue hasn't been reduced. So by adjusting the weight coefficient to match, we can further reduce the residue error of these samples, thereby breaking through the accuracy limit. The relationship between population variance, samples, and weight coefficients is shown in the second step by defining an interval with upper and lower bounds. Centered on expectations, we can categorize fused random variables into two sets. For samples outside the interval, variable weight coefficients can be adjusted to bring them back within bounds, thus reducing population variance by decreasing the residue error of these samples outside the interval. Based on this variable weight fusion, we propose the expectation cluster interval fusion algorithm. This is the framework of this work. First, multiple gyroscopes are fused by MVF. This is minimum variance fusion. Then the estimated expectation is calculated by least squares. The upper and lower bounds of the interval are calculated. Lastly, gyroscopes are fused by a group of new weight coefficients. This algorithm process are as follows. First, outputs from multiple gyroscopes are initially fused by the minimum variance fusion to reach the current accuracy limit. Then the expectation of the fused output is estimated using a least squares method with a sliding window. Next, a cluster interval is created using this expectation and the extreme values in the windows. Finally, if the MVF output falls outside the interval, weight coefficients will be calculated based on the difference between gyroscope's outputs and the expectation. If the MVF output is within the interval, the weight coefficients remain unchanged. Here are the results of our experiments. This is the gyroscope array used in our study. The comparison of the interval bounds, the fitted expectation, MVF outputs, and the ECF output shows that the amplitude of the red ECF output is smaller than that of the blue MVF. The comparison of the original output signals and the ECF results is shown in the left figure. The standard deviation of this work is 0.0057, while the STD of the original signals is improved by 6.6 to 10.1 times. The STD of the MVF, which represents the accuracy limit, is 0.0106, showing a 1.9 times improvement. The Allen variance for the different fusion methods is shown in the left figure. Where the angular rate work of low frequency signals is reduced, will one reason the Allen variance doesn't decrease in there may be that the inability to fit high frequency signals. The STD angular rate frequency based on corresponding fusion methods and KF is shown in this figure. It can be seen that the accuracy of this work is higher than other corresponding fusion methods and KF at different angular rate frequency. Amplitude angular rate frequency based on KF and this work is shown in this figure. It can be seen that the amplitude of this work doesn't reach -3 dB, which means that the bandwidth is not reduced. That concludes my presentation. Thank you.